Why don't we start? So last lecture about privacy and security, and just so that it won't all be about privacy, I'll talk a little bit about security today, but the theme tying everything together is going to be randomized methods and the importance of randomness, which we saw in all these talks about privacy. The random noise, really what we need in order to ensure privacy is to have a stochastic or probabilistic algorithm that outputs a distribution that let us get privacy, and here we're going to see that it's going to let us get verifiability in a very strong and robust way. So I had this ambitious plan for the week, and we spent a little more time on privacy than I had planned. I'm happy we did. Today what I want to talk about is verifiability, verifying the correctness of computations. That'll be the topic today. And secrecy, which is, so part of my point, or what I want to get across, is both in the talks about privacy and in talking today about verifiability, is that these are maybe not what you might traditionally think of as cryptography or security research. It's not encryption, for example. And I won't get to talk about secrecy, but I saw already in the program that you'll have some cryptography speakers, so I'm sure they'll tell you a little bit about secrecy and research on things like encryption and fully homomorphic encryption, which I'll mention today, and some of the other topics that the crypto community has been focusing on recently. But today what I want to talk about is this tantalizing application or idea or motivation of delegating computation. And the idea is, the reality we have today is that all our devices are very weak. They're connected to this cloud. So I can't give a whole week of talks without saying something about the cloud. So everything is connected to the clouds. Interesting computations are all being shipped and conducted remotely. And the setting I want us to think about today is we have this weak client. This isn't so weak, but think about it as your cell phone or even your connected device. It has some function f it wants to compute. It can't compute it on its own, and so it's going to send its input over to the cloud and get back the answer y, which is supposedly f of x. So that's all nice, and that happens all the time today. So anytime you pull out your cell phone, that's probably happening. But the question is, as these computations are becoming more numerous and more sensitive, can we really trust this cloud? It might be buggy, it might have some financial incentives, it might simply be maliciously corrupted. So it might be this scary, stormy-looking cloud. And this brings up a lot of security questions that have been a big focus of research in the crypto community in recent years. And the two concerns that I'll bring up today are correctness. So if the cloud says that f of x is equal to y, do I know that's true? How do I verify this? For example, if I want to run some analysis to decide what stock to buy, and I run it on Amazon servers, and the analysis comes back and says buy Amazon stock, do I trust it? Do I not trust it? So that's correctness. The second concern that I won't talk about today is privacy. So in this setup, usually what happens is that we send our input to the cloud, x in the clear, and it computes f of x. That's a big question for secrecy or privacy. I should say secrecy, not privacy, to distinguish from what I've been talking about in the last few lectures. And there's a lot of research that's been happening on that, both on fully homomorphic encryption, if you've heard about it, and also on oblivious RAM schemes. You may or may not have heard about. I only have an hour today, so what I'll tell you about is this question of verifying correctness, which is what I've been doing somewhere. I've been working a lot on this in the last couple of years, so I'll subject you to hearing about that. So the goal is to allow this client to verify the correctness of the result without running the computation itself. Okay? So we want both the verification to be super efficient, but we also want the procedure of proving, of convincing the client that y is equal to f of x, the algorithm being run by the server, to be efficient, or at least polynomial time. Okay, and this is the question that's known as verifiable computing. So again, we have this client, it has its query, and what we want now is that when the server says f of x is equal to y, it also attaches a proof, sort of a machine verifiable proof that this is indeed the case. So what do I mean when I say proof? I mean, we have a certain notion, intuitive notion of proof that we talk about. Technically what I mean, or technically what I'll want, is completeness and soundness, the usual notions from proof systems. So if the cloud is behaving honestly, if y really is equal to f of x, there should be a procedure for generating a proof that makes the client accept. Okay. Obviously, we want the cloud to be able to help us, so it should be able to convince the client that y is equal to f of x. The more interesting property is soundness. If y is not equal to f of x, if the cloud is lying, then it should not be able to generate a proof that convinces the client. And looking ahead, we'll talk about NP proofs and different kinds of proof systems, but I already want to bring up this issue of randomization. So I'm going to allow the client to be randomized, and I want it to reject with high probability. So if y is not equal to f of x, there shouldn't be any proof that makes the client accept with non-negligible probability.
So maybe this is obvious, but wouldn't it be more desirable to accept with high probability and reject with probability 1? Or maybe that's just impossible?
So it would be really desirable to always accept and always reject, and that's what you get with NP proofs. But what we'll see today is that those proof systems give us stronger guarantees, but they have pretty restricted expressive power. So there are things we simply provably, or not provably because we don't really know anything provably about computational complexity, or we don't know much, but under reasonable assumptions such as p different than np, polynomial hierarchy doesn't collapse, we can't get these kinds of proof systems using the classical notions of NP proofs. So we need randomization. I'll get to it. So that's the notion, what I mean by a proof, what I want from a proof to be convincing. Also, what's really important here is efficiency. So the work done by the client to verify this proof should be much, much smaller than the complexity of computing f. Right? Otherwise, what's the point? The whole point is that the client doesn't want to compute f, it doesn't have the resources, so verification should be super efficient. The flip side to that, which often, especially in complexity theory, we don't talk about, is what's the complexity of generating this proof? Okay, so where does this proof come from? Who is generating it? Of course, I want that to be efficient as well, and hopefully generating the proof isn't much more computationally intensive than just computing the function f. Okay, so we can really use these systems in practice. But certainly, I want the complexity of generating the proof to be polynomial so that we can run these systems in reality. So that's my notion of proof systems. It already came up, but I want to contrast that, or I want to talk for a minute about NP proofs, which I assume most of you have seen. So in an NP proof, you can also think about that as having, we have a verification procedure, we have an untrusted prover, which is just going to send us a proof. And the claim being proven is that an input x is in some language L. So maybe x is a graph, and the claim is that it's 3-colorable. Okay? So you can think of the input as being the graph, and f of x is simply saying whether it's colorable or not colorable. Okay, so it's a Boolean function. But in complexity, we usually talk about languages, which you can simply think of as Boolean functions. And I'll talk mostly about languages in the talk today, not always, but mostly. So language is some subset of all the possible inputs. So for example, the subset of graphs that are 3-colorable. And an NP proof is just a string that's sent. You can think of it as being sent by the prover or written down by the prover, and it's a proof that the input x is in the language L, that the graph is 3-colorable, so maybe it's a 3-coloring of the graph. Completeness in NP proof system says that if x is in the language, there exists a proof that makes the verifier accept. Okay, so if the graph is 3-colorable, there exists a 3-coloring, and we can check that the 3-coloring is valid in polynomial time. Soundness, so going back to your question, soundness says that if the input is not in the language, then there doesn't exist any proof that makes the verifier accept. So every cheating proof, or every candidate proof, will be rejected by the verifier. If the graph isn't 3-coloring, there simply isn't 3-colorable, there simply isn't a coloring that will make us accept it. Okay, so there's no probability. There's also, looking ahead, there's no interaction. And the question about these proof systems, so of course, NP proof systems are central in computer science, especially in theoretical computer science. And yes, the example that I want to carry with us is satisfiability. So given some Boolean formula, say some 3CNF, I want to know whether there's an assignment that satisfies it. Okay? Whether there's an assignment that satisfies the formula. Of course, if the formula is satisfiable, then there exists an assignment and it convinces the verifier. If the formula isn't satisfiable, then no assignment satisfies the formula, and the verifier will always reject. So it's a central question, P versus NP, central to the study of theory and of computation at large. But when I'm looking for what we call doubly efficient proof systems where verification is efficient, but also generating the proof for the honest prover is efficient, the theory of NP proof systems doesn't help us. Okay, so the graph may be three-colorable, but the whole point is that finding this three-coloring is very hard. No one can do it. And that's why we relax the notion of a proof system in order to get results and actually have the proofs be able to efficiently generate the proofs. So in order to do that, what I'm going to do and what I'm going to focus on today is the notion of interactive proof systems. This was introduced by Goldwasser, Micali, and Rakoff in their famous work, also in a different formulation by Babai and Moran. And now these are proof systems that allow interaction between this prover and the verifier. So the verifier and the prover can talk to each other. It's a protocol. They can send messages back and forth. And the verifier is going to be randomized, and that's crucial. Okay? If we let go of either of these restrictions, so if we don't allow the proof system to be interactive, or if we don't allow the proof system to be randomized, then we can't really get the types of general results that I'll talk about today. Okay? So the proof is now in the form of a protocol between the untrusted prover and the verifier. The verifier can ask questions. And the point is, the way randomization is used is that the prover doesn't know in advance what the verifier is going to ask. So the verifier can ask one question, the prover gets an answer, and the prover doesn't know what the next question is going to be in advance. So there's no secrecy here, but it's more an issue of unpredictability. The prover doesn't know what's going to happen. Okay? And now to prove the proof that the input X is in the language L is an interactive protocol, and the verifier is convinced if in the end of the interactive protocol it accepts. Okay? So completeness, as usual, as before, means that if the claim is true, if X is in the language, then there should be a strategy for the prover to follow in this protocol that will make the verifier accept, say always, with probability 1. Soundness, again, always a little more tricky, means that if the input is not in the language, if this claim is false, so think about this as f of X is not equal to Y, then for any cheating prover strategy, okay, for any cheating strategy that the prover might follow, and notice this is what we call always information theoretic security. So there's no computational assumptions about the power of the prover. Whatever it wants to do, whatever strategy it wants to follow, as long as it can't predict the future, as long as it doesn't know what coins the verifier is going to toss, the verifier should reject with probability at least a half in interacting with the prover. And the probability is just over the coins of the verifier. Since the prover is unbounded, you might as well think of it as being deterministic, the cheating prover. It's unbounded, so you might as well think of it as deterministic. So interactive proofs were introduced by Goldwasser, Micali, and Rakoff. Actually, their motivation was for secrecy, and they introduced these in order to get zero-knowledge proof systems, so proof systems that convince the verifier of the validity of a statement, but don't convey any further information. So I think I was planning to talk about that a little bit in the next talk, but there won't be a next talk, so I'll say it briefly now, or I said it briefly now. And they've had a tremendous impact, interactive proof systems, both in cryptography and in complexity theory. And one of the celebrated results about interactive proof systems is that, in fact, these relaxations are very powerful. So they allow you to prove lots and lots of statements. This is the famous IP equals PSpace theorem by Lund, Fortnow, Karloff, Nissan, and Shamir, saying that any language or any function that can be computed in polynomial space, which is much richer even than the class of NP statements, has an interactive proof with a polynomial time verifier. So that's kind of an amazing statement, and maybe it doesn't quite sink in what it means. So an example that I'll come back to later in the talk, think about proving unsatisfiability. Okay, so we have a formula. Before we said, if you want to prove to me that the formula is satisfiable, that's very easy. You just send me an assignment, I check that the assignment satisfies the formula, and I'm convinced. But how would you prove to me that the formula is unsatisfiable? Right? At least a priori, it's not clear. I would need to check every single assignment in order to be convinced that there's no satisfying assignment. And indeed, we know that unless the polynomial hierarchy collapses and our worldview in theoretical computer science is very wrong, we know that there's no NP proof system for unsatisfiability. It's a co-NP complete problem. But what the IP equals PSpace theorem shows is a proof system, an interactive randomized proof system that can be used to convince a verifier of the unsatisfiability of a formula. And I'll actually show you that proof system later in the talk. So what I want is these doubly efficient proof systems, and we'll use, that's sort of a new use of interactive proof systems in order to get this doubly efficient property. What we want is that the strategy for the honest prover can be computed in polynomial time. Okay, so the honest provers, the verifier asks questions, and the honest prover can compute the correct answers just in polynomial time. Note that in this IP equals p space result and in all the classical work, even for polynomial time statements, the honest prover ran in super polynomial time. Okay, so that's sort of a new question. We started tackling, this is in work with Goldwasser and Kalai, where we get these doubly efficient interactive proof systems. Honest prover is polynomial time. I'll emphasize again that we don't make any assumptions about cheating provers. So cheating provers might as well be exponential time. Okay? But for the honest prover, I want the protocol to run in polynomial time. Verifiers are super efficient. And because the honest prover runs in polynomial time, if you think about it a little bit, that means that the honest prover can, in polynomial time, convince himself whether the input is in the language or not. And so we focus on polynomial time computations. I mean, you can only get polynomial time honest provers for polynomial time computations. So the goal is for the honest prover to be polynomial time, but the verifier to be much more efficient than that, say linear time, small space, small depth. We'll even see sublinear time today. Okay, and by now, we have kind of a rich theory of these doubly efficient interactive proof systems. So we can get verification in, this is constant depth, log space, small space, and in linear or sublinear time even for very rich families of statements, so for low depth computations and even for low space computations. This is very recent work with another Rothblum and with Omer Reingold. Okay. And beyond the sort of theoretical cryptographic work that's been done on this, there's also been a growing systems security literature. There are a couple of startups now that are doing creating these types of systems.
Okay, what are the assumptions for the last slide? Can you say something?
There are no assumptions.
Oh,
Everything is information theoretic.
Huh?
Everything is information. We're talking about information theory, right?
Okay.
Yeah, it's not cryptographic. There are no cryptographic assumptions anywhere. So you can actually get, if you want to make cryptographic assumptions, you can get even richer classes of computations by making cryptographic assumptions. Actually, one of the things about those protocols, I mean, besides the fact that as theorists we don't like making assumptions, using cryptography also has a pretty heavy overhead in practice. So the most efficient protocols in this literature that build systems are actually the information theoretic ones. Because all they do is operations over finite fields.
Does the first line of your slide, it seems like, does that change if you have a lot of assumptions? Can you make it any faster? Or
Which one, what line?
is the first line, verification has zero?
No. No. Okay, yeah, so there's actually, I mean, there's a couple of startups, there's a bunch of systems works, and you can see the conferences, so I mean, I think this really is a place where the work that started in theory is having a broader impact, which is always nice. Okay, so let me quickly tell you about these results, and then what I want to do is give you sort of three vignettes from research in this field. Or from this body of work. So, but I want to focus on a couple of these results first. So, linear time or quasi-linear time verification. So, this is a theorem with Goldwasser and Kalai from that first paper. Show that every language computable. Sorry, I forgot to replace this. This should be n to the alpha. So, any language computable in depth n to the alpha. So, small polynomial depth for alpha that even approaches 1. Or actually, this is for any alpha as it's written here. We have an interactive proof. So depth here, by the way, how many people are familiar with sort of Boolean circuit depth? You've seen this? Yeah. So depth is Boolean circuit depth for computing the language or the function. And every such language has an interactive proof where the prover is polynomial time as we wanted it. The verifier is almost linear time. So depending on what the depth is, if the depth is polylogarithmic, the verifier is quasi-linear. And the communication is small, the number of rounds is bounded.
Okay. The depth is n to the alpha?
Yeah.
So the size of the circuit
The size of the circuit can be n to the 100. Yeah, it can be n to the 100 or... Oh, no, sorry, this is polynomials, I should say that. Polynomial size, depth n to the alpha. In general, the verifier is logarithmic in the size, and the prover is polynomial in the size. So this theorem scales up to bigger sizes, but I'm stating it here for polynomial size circuits. So comparing that with, I told you about this celebrated IP equals IpSpace theorem, the main difference is in the time, the running time of the honest prover. So the honest prover here is polynomial time, whereas if you just scale down the IP equals IpSpace theorem, you would get an exponential time honest prover. Okay, even if you scaled it down to bounded depth polynomial size circuit families. It would give you something, but it... so in particular, the IP equals IpSpace theorem is tight in terms of the verification time. So it tells us tightly what the verification time needs to be. It's also tight in terms of the communication. It isn't tight in the, it's very inefficient. It's exponentially inefficient as far as we know in the running time of the honest prover. And as we'll see, it's also very inefficient in terms of the number of rounds.
So maybe versus IpSpace, is it 2 to the n or double exponential?
2 to the n, for here it would be 2 to the n to the alpha for this example, 2 to the depth.
But isn't it the best it can be?
Nope, so you see. Yeah, it is. So it is if you, sure. So basically what happens in the IP equals IpSpace theorem is that the running time of the honest prover, if the computation, if you're looking at a computation that runs in time t and space s, the honest prover runs in time t to the poly s. Okay? So yeah, if you set this to be, if you're looking at IpSpace and this is say 2 to the n and this is poly n, then you get a 2 to the poly n prover and you say, well, I can't really hope for better. But if you scale this down, I mean, this isn't tight. Yeah. Okay. So one thing that's interesting here is that also we had to look at, I mean, we had to circuit depth is interesting, but in IP equals IpSpace, you know, it related the space of the computation. It looked at Turing machine computations, related the space, or used the small space of the computation to get an interactive proof system. We couldn't do that in this work. And also we have lots of rounds, both here and in the IP equals IpSpace theorem. The number of rounds depends on the space, or here the depth of the computation. And again, it's not clear that it was never clear that that's inherent. So we have some recent work. That's with Ron Rothblum and with Omer Reingold, actually addressing both of these open questions. And there we show that for any language that's computable in bounded space, so now in space n to the alpha and polynomial time, we have an interactive proof system where, again, the honest prover runs in polynomial time. The verifier is quasi-linear, assuming alpha is small enough. So alpha is, say, something like a third or a half, at most a third or a half. The verifier is quasi-linear. And now the number of rounds is constant. Okay, so instead of a polynomial number of interaction rounds, it's constant. I mean, that's significant because if you're running the protocol, rounds of interaction have latency, and so it's interesting in theory. It's also interesting in practice. The communication is optimal. I mean, this is the best you could hope for it to be. So here it improves, or for this regime of parameters, for bounded space and polynomial time computations, you know, there's both an exponential improvement in the prover, comparing the IP equals IpSpace theorem. We both address we get a tight dependence of the prover's running time, we get a tight honest prover running time, and also a tight number of rounds of interaction. So this is optimal, you can't do better.
Space and the alpha and polynomial time as well, right?
Yeah. So simultaneously, space n to the alpha and polynomial time. So any basically computation that you can run in bounded space.
It's depth d. Do you get like space? You can compute any depth d.
No, so it's incomparable. So that's a great open question. The relationship between polynomial time bounded space computation and polynomial size bounded depth circuits, we don't know. This is NC and Steve's class, SC, yeah. This is a big open question. We don't know what the relationship between these two complexity classes is. If you don't restrict to polynomial time, then these two things are equivalent. So bounded depth with unlimited circuit size and bounded space with unlimited running time are equivalent. But once you make the restriction to polynomial size or polynomial time, we don't know what the relationship is. So these,
This is stronger.
no, incomparable.
Oh, because you have polynomial time aspect.
Yeah, incomparable. Yeah, and it's, I will say that if you scale it up to IP equals p space, you don't quite recover the IP equals p space theorem. So it's also incomparable to this one. In particular, the verification time is a little bit more than what you get in the IP equals p space theorem. We have some follow-up work on that, but it's, as it is right now, it's not quite tight. But for the regime of parameters we're interested in, polynomial time bounded space computations, this is tight. So this gives us a full understanding of what's going on. Okay, the last thing I want to talk about, and then we'll go to actually see some technical stuff and a couple of cool techniques from this literature, is sublinear running time. So in both of these results, the verifier ran in, that made us very happy. It was just linear in the input length. But of course, you might hope for better. We're computer scientists, we're always greedy. If we can do it in linear time, then we want to do it in sublinear time. And here, in particular, that's very appealing. So we could think about, in the scenario of delegating computation, we could think about a big data input. So think about something like the Twitter graph or some big logs that you have as a corporation. And you want to run some statistical function on this data. So you have some statistical query over the big data that you want to run. You don't, maybe it's even computable in linear time, but linear time is too much with big data. So what you'll do is you'll ask this untrusted cloud to compute the function for you, and then you want a proof. And you want to be able to verify the proof in sublinear time using random access or query access to the input. So that's what it means to run, to verify a computation, or to verify a computation in sublinear time. Now, of course, if you think about it a little bit, suppose, for example, that you wanted to compute the parity of all the bits in this input x. There's no way that I can convince you that the parity is 0 unless you read each and every bit. That's easy to prove. Okay, so there are easy functions for which you can't have sublinear time verification that y is exactly equal to f of x.
X is in the client side or on the server side?
It's out of either one of their control. Neither one of them. They can both read it, but neither one of them actually. I mean, the cloud needs to read the entire input x. But the client just has query access to it, and I do assume that the cloud can't change the bits of x. So x is fixed, and then the client can query bits of it. But still, if you want to, for example, verify that the parity of all the bits is 0, you can't do it without reading each and every single bit. That's easy to show. But that's also not an interesting, that might seem discouraging, but it's not really an interesting counterexample, right? What we really want on big data is to compute statistical functions. And when we talk about sublinear time algorithms, what we always want is an approximate guarantee of correctness. That's what we'll do also here in terms of the so the completeness guarantee is going to be exactly as before, but when we talk about catching a cheating prover, we're going to ask for approximate soundness, so for verifying approximate correctness. And in particular, what we want is that if f of x is far from y, so if the cloud sends y which is far from f of x, then the client should reject with high probability. So what do I mean by far from correct? I mean that you would need to change many bits of x in order to get to an x prime where f of x prime is equal to y. Okay, so x is at large Hamming distance from the claimed value y. And with this, so this is a relaxation to soundness, right? If the cloud or the prover is cheating by a little bit, then we're not guaranteed to catch that, and that's fine when we run in sublinear time. But what we gain is that the client work is going to be much smaller than the size of x, and of course much smaller than the complexity of computing f.
This only makes sense for functions that don't look like parity.
Sorry, that don't look like parity, yeah.
What kind? Is there
Every statistical function, everything you actually want to compute on big data.
what is a statistical function?
Something that has low sensitivity, for example. So something where, anything where you would hope to have a sublinear time algorithm even, right? Like everything and more, but everything you could hope to get some idea of by sampling, by looking at a little bit of the input, where essentially where changing one bit of the input doesn't completely change the value of the function.
Or just probably any function if f is encoded.
That's right, yeah, that's right. But if x so I should say that if x is encoded using an error correcting code, you can get exact soundness. And in fact, this was known by the previous literature. That plays an important role in some of the previous literature. So if you assume X has a certain format, then things become much easier. But here we're not making any assumptions about the format of X. Yeah, it's a very good observation. Good point. Yeah, so...
It's not any function where X is encoded, but then you would have to have F behave well around the code.
Yeah, so then F has to decode, right?
No, F is applied to X, but what we accept, but the available is error-correcting code of X.
Yeah, so what Anoop is saying is you can...
It would be the same.
What Anoop is saying is that you could think of that as F decoding X and then computing F on the decoded thing. Okay. So what these are called are proofs of proximity. So basically you're proving proximity to a language. If X is in the language, then as before, the verifier should accept. And for soundness, we say that if X is epsilon far in Hamming distance from the language, meaning you would have to flip an epsilon fraction of the bits in order to get to an input that's in the language, then the verifier should reject with high probability no matter what the prover, no matter what a cheating prover does. And I want to emphasize here that we're measuring the number of queries the verifier makes to the input. We're measuring the bits of communication, the number of rounds. All of these should be sublinear. Sorry, the honest prover running time is not sublinear. That's polynomial. But the verifier's queries, communication, running time, all of those need to be sublinear. And then kind of building on, well, so this is a result with Vadhan and Vigdersen, but you can also plug in the new result for bounded space computations. And that says that for any epsilon, so for any approximation you want, that's at least 1 over root n approximation. So 1 over root n, if you want 1 over root n accuracy or 1 over root n distance, then every language that's computable in bounded space, as before, has an interactive proof of proximity. And now the verifier runs in essentially square root of n time. Okay, so square root of n, or something close to square root of n, queries, square root of n communication, constant number of rounds. Verifier running time is close to square root of n. So it's a very general statement. And I think in that, I want to contrast that with what happens with sublinear time algorithms, where we don't have any general statements, where if you want to build a sublinear time algorithm, you have to look at the function you're trying to approximate. You have to leverage some algebraic structure, some combinatorial structure, some geometry, something. And you just have to sit down and design a sublinear time algorithm or prove that one doesn't exist. Here, all we need to know is that the language is efficiently computable. We don't need to use any of its particular structure. So this is very related. Maybe I'll sort of gloss over that. But it's very related to property testing, if you know what that is. It's very related to sublinear algorithms. But as I said, in that field, sort of the difference from that field is that there you have to go on a problem-by-problem basis. And many problems don't have property testers, don't have sublinear time algorithms, whereas here we can get general results. And
Do you have any characterization of what can be done?
I think the short answer is no. That's a good question. So I didn't say it, but I should say that there are languages computable in small space and small depth that require, provably under some assumptions, they require root n communication and queries. So this is tight if you want to talk about general, but I don't know of a characterization for which, a characterization for all the functions or all the languages that have sublinear time proofs. Okay, and there are other related models, but let's not talk about them. What I want to do in the remaining time is kind of give you a taste of 3 techniques that power these results. And the first one is this classical work, the Subcheck protocol, and a way of verifying that a formula has no satisfying assignments. So we talked about that problem before, and we'll see the protocol. And I think it's a cool protocol. It underlies basically everything or a lot in modern complexity theory. So the PCP theorem, IP equals P space, a lot of cryptographic protocols. So it's a very central protocol, and we'll see that today. I'll tell you a little bit about how to verify the correctness of low-depth computations, if we have time. And then I want to give you an example for sublinear verification that I think is appropriate, so verifying the Hamming weight of a string, how to do that in sublinear time. So the Subcheck, basically what I want to show you is we have a Boolean formula, okay, so it's over m variables. These variables take values in 0, 1, and the formula is a Boolean formula. Maybe it's even a 3CNF, so it has, these clauses that look at, it checks whether either Z1 is 1, or Z5 is 0, or Z9 is 1, and this other clause also holds if yes, then it outputs 1, and if not, then it outputs 0. Just a standard Boolean formula. What we want to prove is that no assignment satisfies it. So for every assignment in 0, 1 to the m, the formula outputs 0. Okay. We want a proof. This is the prover's claim, and we want a proof of it. In order to prove it, what we do, or the way this works, is by an algebraic view of this formula. And that's really important in this whole literature, is we take computations and we algebraize them. We take an algebraic view of the computation, and here in particular we'll take this, poor innocent Boolean formula, and we'll force it to be a polynomial. So we'll think of it as a low-degree polynomial over some very large field. Okay, some very large finite field. And you can do this using, using standard, so you replace ands with multiplication, and you replace negation with sort of 1 minus operations. So using finite field arithmetic, you can simply view this as a polynomial of low degree over a very large field. Okay? And then the formula is unsatisfiable if and only if the sum over all possible assignments, looking at this formula as a low-degree polynomial, the sum over all possible assignments of the formula's value is equal to 0. Okay, so I won't get into the details of why this is true, but you'll believe me that we can look at the formula as a low-degree polynomial, and taking a sufficiently large field, the formula is unsatisfiable if and only if this algebraic equality holds. So basically what the prover is going to do is prove that this sum, this big exponential sum, so to compute this sum takes 2 to the m time, right? Because you have to enumerate over all the possible assignments. And the prover is going to prove that this exponential sum is equal to 0.
But phi can actually be described as a small description.
Yeah, sorry. So evaluating the polynomial, so certainly evaluating the Boolean formula can be done in polynomial time. It's written down for us. And also, transforming it to a polynomial and evaluating that polynomial all over the field can be done in polynomial time. And in particular, all that the verifier will do in this protocol, it's only going to evaluate this polynomial at a single location. It's going to do a single polynomial evaluation. Rather, it's going to verify 2 to the m evaluations using a single evaluation. Okay. So what does this protocol look like? The prover's claim is that 0 or some y is equal to this big exponential sum. And the protocol is just going to use low-degree polynomials. And every round, the prover is going to send a single-variate polynomial to the verifier. Okay, so a single-variate low-degree polynomial, that's something small. The prover, we can describe it certainly by a number of field elements that's equal to the degree. And the prover sends in every round a single-variate polynomial to the verifier. And the first polynomial simply has the first variable free. Okay, so it's g1, and it's a polynomial in the first variable, z1, that just computes the sum over all the remaining m-1 variables of the assignment that begins with z1 and then has the rest of these variables plugged in. Okay, so that's well defined. That's simply a univariate, low-degree polynomial. It requires time 2 to the m-1 to evaluate it, but I'm not worried about that. That's the prover's job. So he can evaluate this polynomial, he can interpolate, and he sends the coefficients to the verifier. That's a small description. And so what's the verifier going to do when it gets this polynomial? Any ideas? So first thing it should do? Pick Z1 at random. But yeah, you should check, first of all, you should check that this is consistent with the prover's claim, right? And that's easy to check. What the prover is basically claiming is that if you plug 0 into this polynomial, then sum over all the remaining suffixes, and then you plug in 1 and you sum over all the remaining suffixes. If you add that together, then you've summed over all the Boolean assignments to z1 up to zm, and that value should be y. Okay, so the verifier just checks that this equality holds. He plugs 0 into this polynomial, he plugs 1, adds them together, and he sees that it's consistent with the prover's past claim. Otherwise, immediately reject. Clearly something fishy is going on. And then, as was suggested, if this test passes, then the verifier just chooses a random assignment to the first variable. We fix that, And now in the next round, the prover is going to send, the first variable is fixed, and the second variable is going to be free. And the prover is going to sum over the remaining suffix of m minus 2 variables, or the remaining variables that haven't been fixed and that aren't free here. So he sends this polynomial gi in the ith variable zi, where the 1 up to I minus 1 variables have been fixed to random values chosen by the verifier, and we're summing over all the remaining variables. Okay, so that's in the ith round. And again, the first thing the verifier does when it sees this polynomial gi is it verifies that it's consistent with the previous polynomial sent by the prover. Okay, so it looks at the value of gi at 0 plus the value of gi at 1, and it checks that it's equal to the previous polynomial sent by the prover at the random coordinate that it chose. Okay, clearly, if the prover is honest, this should be the case. And if this test doesn't hold, the verifier should immediately reject. The prover isn't being consistent with its own claims, and the verifier should reject immediately. So this goes on for m rounds. In every round, the prover sends a single polynomial, the verifier sends a single field element, and then in the end, in the last polynomial, all the variables are fixed to random values. Only the last variable is free, and the verifier simply checks that if it chooses a random coordinate for this last value, so it checks the last polynomial in a random coordinate, that's consistent with the actual formula phi. So this is the only place where the verifier is actually going back to the real formula and checking consistency. Okay, so it's doing one evaluation of this original formula phi. So the protocol makes sense? So one thing you should be convinced of is that this is complete. Okay? If the prover follows the protocol, is sending the correct polynomials, all of these checks, everything should be consistent and the verifier should accept. Okay, there's nothing clever happening with completeness. The only question is, what about soundness? I mean, is this in fact a sound protocol? Okay, so remember again, so to prove soundness, remember the structure of the protocol. In every round, the prover sends a polynomial in the ith variable, and then the verifier fixes the ith variable to some random value. And suppose now for soundness that the prover is making a false claim. So it's claiming actually the correct sum is some y, but the prover is claiming that that the sum is some y star. That's not the correct value. Okay? And suppose, moreover, that somehow this p star manages to get the verifier to accept. Okay, so it sends some polynomials, not the correct ones, not the correct sums of the formula phi, but some false polynomials. I mean, some of them may be false, some of them may be true, but it's sending a sequence of polynomials, and in the end, the verifier accepts. Suppose the prover manages to do this. Then I claim that there must be some round between round 1 and I, such that the prover is sending the wrong polynomial. Right? So in particular, in the first round, it has to send the wrong polynomial, because the right polynomial doesn't sum up to y. It doesn't sum up to y star, it sums up to y. So in the first round, it has to send a cheating polynomial, like the wrong polynomial. But in the end, it's getting the verifier to accept, right? In the last round, the verifier is checking the consistency of the last polynomial with the real formula. Okay, so the prover must have been sending, if this check passes, the prover must have been sending, or with all but small probability, the prover must have been sending the correct polynomial in the last round. So there has to be some round where the prover is going from a false polynomial to is sending a false polynomial, but somehow is going to the correct polynomial, and in particular, the polynomial that it sent and the correct polynomial have to agree on this random challenge Ri chosen by the verifier in that round. So if the prover is getting the verifier to accept, there must be some round where it sent the wrong polynomial, but somehow this polynomial agrees with the correct one on the verifier's challenge. But the whole point is that the prover sends its polynomial before it knows what the verifier's challenge is. Right? That's the whole. It doesn't know in advance what the verifier is going to ask. And since we have here two low-degree polynomials, we know that they differ almost everywhere, just by the Schwarz-Zippel lemma. In particular, the probability that the prover manages to send a wrong polynomial that magically agrees with the correct one in a random location is very small. Good. And really the only thing we were using here is low degreeness of these polynomials. So the protocol works for any low degree polynomial, and it's important because you need this for the Schwarz-Zippel lemma in order to say that this can't happen, in order to use the Schwarz-Zippel lemma.
We do not need actually Schwarz-Zippel because we have polynomials with one layer.
Sorry?
We do not need Schwarz-Zippel because we are using...
I agree. I agree. So I'm making the sin, I'm committing the sin of computer scientists that attribute everything about polynomials to Schwarz-Zippel. And yeah, you're right. It's just a univariate polynomial. So all we need is that the number of roots is bounded. Okay, so that's verifying that a formula. Now we've managed to verify using an interactive protocol that a formula has no satisfying assignments. I'll quickly tell you about the structure of this GKR interactive proof for verifying low-depth computations. I won't go much into it. I'll just tell you generally what the structure is and how it builds on this Subcheck protocol. So the idea is, in this proof, we have a computation that's described by a very big circuit, right? And we want to verify that the output, so it has some input x, and the prover is claiming that the output is some y. And we want to verify that if we actually ran this big Boolean circuit, so it has low depth, but it's very wide, a big circuit, we want to verify that indeed if we ran this circuit on input x, we would get the output y. In order to do that, we just think about if we were to run the mental experiment, think about running this circuit on input x and divide the circuit into layers. Okay, so it's a bounded depth circuit. It has at most d layers. It looks like this. And think about the assignment that the gates at every layer can get. Okay, so we have a Boolean assignment for every one of the layers. In the input layer, the assignment is just the input, and then we compute up the circuit. Okay, and we're thinking about this. We'll think about this as an arithmetic circuit again over a finite field. So it has addition and multiplication gates. And the way the computation works, it's a load-up circuit. So once we specify the input in one parallel step, we can compute the entire assignment to the next layer up, and then the next layer up, and this goes on up the circuit until we get the output after d parallel steps. Now the idea in the interactive proof is to unwind, the circuit computation goes from bottom to top. The interactive proof is going to go from top to bottom and unwind the circuit computation. What we're going to do is reduce proving the value of one location in the encoding of an advanced step. So we'll use error correcting codes as that was a good idea that was hinted at. And we're going to think about encoding each of these layers of the computation, and we'll reduce from proving the value of one location in the encoding of an advanced step, of a step high up, to proving the value of one location in the encoding of an earlier step. Okay, so in the beginning, we're going to have this reduction, this interactive reduction. In the beginning, the prover is making a claim about the encoding of step I, layer I, a tall layer in the computation. Layer I in the computation. And we're going to run an interactive protocol, and in the end, we're going to get a new claim about one layer down. Okay, and the idea is that if the prover was cheating on layer I, it'll have to be cheating in the new claim that it makes. We're going to do this d times, unwind the computation layer by layer, and in the end, all we need to do is prove a claim about the encoding of the input. Okay, the input the verifier has, and it can compute coordinates in the encoding in linear or quasi-linear time by itself, and verify this final claim about the input. So that's the structure of the protocol, of the interactive proof. In a little more detail, we'll use a specific error correcting code, although there have been works now generalizing this to using any linear code, or any code with using any linear code essentially. And in every layer, what we'll have is we'll start with an input. We're going to think of the sub protocol that does this reduction from layer I to layer I plus 1 that's below it. So we're going to start with an input that specifies a claim about layer I, and that input is going to just tell us a coordinate in the encoding of the values of layer I, and a claimed value for that coordinate. And the prover's claim is that if I were to encode all of the values, all of the gates, the values of the gates in layer I, and look in the coordinate Ri, the value I would see is Vi. Okay, that's the claim when we're running this sub-protocol, this consistency sub-protocol. And then the verifier is going to ask questions, the prover is going to give answers. In the end, the verifier is going to output a new claim about layer I plus 1 of the same form. Okay, so it's going to output a claim that says So in the end, it tells the prover, okay, I believe your claim. I believe that the encoding of layer I at location Ri is equal to Vi if you can prove to me that the encoding of layer I plus 1 at location Ri plus 1 is equal to Vi plus 1. Okay? So that's a protocol. That's, this is a reduction, or this is the output of an interactive protocol between the prover and the verifier. And the soundness guarantee is that if the initial claim was false, if the prover was cheating here, then with high probability over the verifier's coins, the new claim that we get as a result of the protocol will also be false, with all but a small error probability. And once we have this consistency subprotocol, we can just run it. We start from the output layer where the prover has completely specified its claim, and we go down layer by layer by layer by layer till we get a claim about the encoding of the input, and the verifier just checks that on its own.
So this error correcting encoding is just kind of virtual. It's not
Yeah, well, so it's a virtual thing. The prover needs to compute it in order to get the answers, but the verifier never does. Yeah, it's all happening in our heads. Yeah.
Is it very different from the polynomials we had before that were also error corrected?
Well, it is. So you do get it by looking. No, I think it's. Well, very different. I don't know. It's related in the sense that what this encoding does is it looks at the function that assigns for every gate, tells you what the value of that gate is. It looks at that function, and it looks at it as a polynomial, and it extends it over a large field. So now it's a low-degree polynomial over a large field, and then we work with that. So it's a different protocol from the previous one, but it also uses a very arithmetic view of the computation. And this protocol, as we at least originally conceived it, really uses a specific error-correcting code, so low-degree extension or the Reed-Muller code, in order to get these consistency properties and be able to get these consistency properties. And there's been some work on getting rid of that, of using codes with different structure, of not relying on that specific code. But I think for today, think about that as that specific code. Okay, so I won't go into the gory details of this protocol. I just want to tell you a little bit about how it's related, or what the challenges are, and how it's related to the Subcheck that I told you about. So again, the goal is to go from a claim about layer I to a claim about layer I plus 1. And notice that you might object immediately and say, well, how are layers I and I plus 1 connected? What's the relationship? I mean, there's all these wires. How can the verifier verify anything without actually knowing the relationship between the layers of the circuit and reading all of these wires? Right? I mean, this relationship is underspecified at the moment. For general circuits, you would really need to read the entire, at least all the wire, just to know how the circuit is wired, what the gates are, in order to verify consistency between layer I and I plus 1. Yeah, so, well, in general, you could think that it's just given to the verifier as a very long bit string, and then it has to read all of it, the circuit. But what we'll use is an implicit representation of the circuit, so we will assume that the circuit is uniform, and in particular, we assume, exactly as you're saying, that we assume there's a Turing machine that could generate the circuit, and the Turing machine is a very small object. So we assume log space uniformity of the circuit. And then we have basically, so as you're saying, we have a function that computes the wiring of the circuit, and in fact this function, with some work, we can get this function to be itself a low-degree polynomial. And then what we do is we represent the encoding of layer I as a large sum of very low-degree functions on the values of layer I plus 1, and on this implicit representation of the circuit that itself is a low-degree polynomial, and we use a Subcheck to verify that the claim being made about this large sum is correct. So the Subcheck lets us verify big sums. All we need to do is represent the encoding of layer I plus 1 as a large sum on the values in the encoding of layer I plus 1. And then we use a Subcheck, and we go home happy.
This is for Reed-Muller encoding, or just for any encoding?
This is Reed-Muller or low-degree, Reed-Muller low-degree extension. They're the same thing. So encodings using multivariate low-degree polynomials. Okay. So I think what I want to do to wrap up what I'm going to do to wrap up is just to give a fun example. Well, I hope it's fun. I hope it's going to be fun for me and fun for you, of how to verify Hamming weight, and to just give you some idea or some taste of what sublinear time verification looks like. This is kind of a toy example. As I told you, we have very general theorems that talk about computations that run in general low depth or low space. But this is a fun example to think about, to just get some idea for how one might use this model or what the power of the model is. So the goal is to estimate the Hamming weight. So what the prover and the verifier both have. Now we're going for sublinear time. So we're in this proof of proximity setting. And the input is a string, an n-bit string of zeros and ones. What the verifier wants is to verify the Hamming weight of this string up to a fractional additive error of 1 over root n. Okay, so a root n absolute error. So for example, I want to, if the prover is claiming that the number of ones in the string is n over 2, I want to verify that it's, between n over 2 minus root n and n over 2 plus root n. So I want very good additive error, and I want to run in sublinear time. In particular, I want to run just in root n time. And we know by sampling bounds that this is completely impossible in the standard model. So to get an additive error of 1 over root n, you have to make n samples, if you're just doing sampling from the string. But using the untrusted prover, we're going to manage to get the running time down to root n. So let's do it. So we have our input x comma y, and the prover claims that the Hamming weight of x is equal to y. Okay, I'm thinking now of absolute Hamming weight, not fractional. So 1 over root n far means that actually the Hamming weight of x is at least root n bigger than y, say. Okay, or is root n away from y. And the way the protocol works is we think about the input x as a matrix, a root n by root n matrix. So that's our input. And what we're going to ask the prover to do is to send the Hamming weight of each row of this matrix. That's the first thing that the prover does. So think about these rows as x1, x2 up to xk. K here is equal to root n, so I'm thinking about this as a square matrix. And the prover, we're asking the prover to send alleged sums for these rows. So the real Hamming weights are these Hamming weights of x1 up to xk. The prover, and the total Hamming weight is of course just the sum of the Hamming weights of all the rows, and the total number of ones. The prover is sending some arbitrary values, some arbitrary weights for the different rows. And now what's the first thing? So this is what the prover is sending. What's the first thing we should do? By now we're used to this. Yeah, verify that the claim is consistent with these individual row weights. Okay, verify that the sum of all these weights given by the prover is equal to its claim, to the Hamming weight that it claimed. Otherwise, reject immediately. Clearly something is fishy. Okay. So the prover has to send us Hamming weights that sum up to the incorrect or to the far away Hamming weight. That means that on many of these, it has to be cheating on these rows somewhere, right? Since we know that the real Hamming weight is much bigger or much smaller, we know that it has to be cheating somewhere here on some of these rows.
But that might be that there is only cheating in one.
Good. So you're very paranoid, but let's start with an easy case, okay? So suppose that he's cheating on many rows. So he's not such a clever cheating prover, and he's cheating on many of the rows.
But then we check a random.
But he's checking, very small. He's cheating by a very small amount, but on many rows. And then, as you're saying, again, you're absolutely right. If he's cheating on many of the rows, say if he's cheating on about half the rows, we can just pick a constant number, a number of rows at random, and brute force check them, see whether the answer is exactly correct. And this can be done since we're only reading a constant number of rows. This only requires root n queries and root n communication, or n log n for sending all of these row sums. Okay, so if the prover is cheating this way, then we go home very happy. As you're saying, the prover might not be so silly, and it might do large cheating on a few rows. In particular, it might just cheat on one of the rows. But if it's cheating on just one of the rows, it has to be cheating by a lot. Right? It can't cheat by a little bit on the row and still be equal to a sum that's far away from the correct Hamming weight. Okay, so if it's cheating on just one of the rows, it's cheating by almost root n. And then what we'll do is we'll check each row isn't very corrupted simply using sampling. So for example, if it's cheating by root n over 2, by reading a constant fraction of the bits of this row, we could detect this using sampling, just using plain old sampling. Okay, so if it's cheating on just one row by root n, or say root n over 2, by simply checking a constant number of bits in each of the rows, we will detect this, and again, this gives us root n queries and communication. So in these two extreme cases, we got root n. Actually, the general case isn't quite as optimal.
So you say that we just probabilistically check all the rows,
Yeah.
and seriously check one, like internal
Yes.
service task.
Yes. So we do a light probabilistic check on all the rows, and then we pick one or a few at random and do a heavy check on them. And in general, there must be some, using this usual trick, there must be some value for which the prover is cheating by at least root n over, by at least r on at least root n over r rows in order to get a total root n cheating. Okay, so there must be some value, we look at all the powers of 2 between 1 and root n, and there must be some r star such that the prover is cheating by at least root n over r star on r star rows. And so what we're going to do is for each of these candidate r stars, we don't know which one it is. The prover could have some cheating. It might be here. So here it's cheating on just one row. Here it's cheating on all root n of the rows. And in general, it could be cheating on some fraction of the rows. So we're just going to try all the possible values for r star. There are only log n of them, or log n minus 1 of them. And for each of those, we're going to check that, we're going to choose root n over r of the rows to guarantee that we get at least one of these rows that the prover is cheating on, and we're going to run the appropriate probabilistic test. So this on its own, as I told you, it doesn't quite work out to root n. On its own, this gives you an n to the 3/4, a protocol with n to the 3/4 queries and root n communication. You can do better by recursively, instead of actually doing the heavy tests, you can just recurse. So run another protocol. Instead of sort of reading the bits by brute force, you run a more efficient protocol in order to do this. And that gives you, using more interaction, that gets you down to root n queries and communication. So you certainly need root n queries. Yeah, so root n queries, if you don't look at root n locations of the input, then it's clear that you can detect root n distance. There isn't a lower bound on the number of rounds, and I don't think there's a lower bound on the communication. So as far as I know, it might be possible to do this with logarithmic communication and root n queries. I don't know the answer to that. There has been work on reducing the number of rounds of interaction. Okay, so that was just an example. So, and I should say that for these interactive proofs of proximity, you can often do, so here we improved, basically, we got a quadratic improvement over what you needed to do without a prover. So you could go from query complexity n to root n using the untrusted prover. We also have examples where we get an exponential separation. So in particular, we have a proof for graph bipartiteness. So checking that a graph is close to bipartite, where we know that there's a sublinear time algorithm, but it runs in root n time. And using an untrusted prover, we can get a logarithmic query and communication complexity. So there are some natural examples, and there's also these general theorems that talk about any computation of bounded space or depth, but we didn't get into that. Okay, good. So that's what I wanted to say about verifiable computing. We have quasi-linear time led to sublinear time, and now we even have constant round sublinear time verification. There's been a lot of work that I didn't talk about on just getting completely non-interactive cryptographic arguments. So using cryptographic assumptions and assuming that the cheating prover can't break some strong cryptography that's in the system. Here we didn't make any assumptions. If you make those assumptions, you can reduce the number of interactions, and you can also get more expressive power, so you don't need to assume bounded space, for example. And yeah, that's all I wanted to say, so thank you.